me see if I got this thing recording. Yeah, okay. All right, so last time we talked about counting gas particles, and we said basically if we know pressure, we know volume, we know the temperature of the gas, then we can count the number of moles of the gas. So one application of that equation would be to determine the molar mass of a gas, because to determine the molar mass of anything, if you recall, what does molar mass mean? It's the mass per mole. So all you need to do is find a way to measure the mass and then divide that by the number of moles, then that gives you the molar mass. Okay, so in other words, if you measure pressure, volume, temperature, and the mass, so this pressure, volume, and temperature will give you a number of moles. So if you have the mass divided by the number of moles, that's going to give you the molar mass per mole. Okay, so let's take a look at an example first. A simple example. Let's say you have a sample of unknown gas with a mass of 0.8802 grams. And let's say you measure the pressure, volume, and temperature of this gas, and you solve for the number of moles, and you found that it's 0.0200 moles in that sample. And what's the molar mass of the gas? Molar mass is just mass divided by moles. So this is going to be 0.8802 grams divided by the number of moles, which is 0.0200 moles. So let's calculate that. 0.8802 divided by 0.02, that gives you 44.01. So 44.01 grams per mole. This has 3 sig figs down here, 4 sig figs up here, so I'm only going to keep 3 sig figs here. I'm going to drop that one right there. So the molar mass of this gas would be 44.0 grams per mole. Okay? Let's look at a more applied example. Let's say you have a sample of an unknown gas, okay? You found its mass to be 0.140 grams, that's particular sample. And for that particular sample, you found that it has a volume of 153.1 milliliters at 100 degrees Celsius, which is 373 Kelvin, and a pressure of 1 atmosphere. Which of these is a possible identity of the compound? So our strategy here is to just say, okay, I know my mass, okay, I know my volume, I know my temperature, I know my pressure, so I can solve for the molar mass. All I have to do then, once I've solved for the molar mass, is to figure out which of these matches that molar mass. Okay, so actually, why don't you solve for this? Solve for the molar mass for me. I'll give you a little time to solve for the molar mass, and then we'll figure out what the answer is. Remember your value for R is 0.08206 liters times atmosphere per Kelvin per mole, okay? Okay, let's go ahead and calculate the number of moles. number of moles is PV over RT. What's our pressure? 1 atmosphere. Our volume is 153.1 mils. So here's our volume. So we need to change that to liters. So that's going to be 0.1531 liters, just to make our units consistent with the units we're using for R. Okay, divided by R, which is 0.08206 liters times atmospheres per Kelvin per mole. And our temperature is 373 Kelvin. Okay, so how many moles do we have? Let's calculate number of moles. We have 1 times 0.1531 divided by 0.08206 divided by 373. That gives me 0.005002. Okay, 0.00, two zeros, 5002. Okay, now I should only have 3 sig figs here, but I'm going to keep that extra digit there since I'm going to use this number for further calculation. This tells me the number of moles. Okay, 6945. I think that might be, is that the molar mass they calculated? Yeah, molar mass would then be mass over moles. Okay, so mass is how much? It's given as 0.140 grams right here. Okay, so 0.140 grams divided by number of moles is 0.005002 moles. And if you did that, I still have that number up there, so divide it by, oops, clear, let me clear this one. Okay, so I have 0.140 divided by 0.005002. That gives me 27.98. And I need 3 sig figs, so that's going to be 28.0 grams per mole. Okay? So now that we figured out our molar mass is 28 grams per mole, which one could it be? Is it A, CH4, B, CO, or C, Cl2? So based on the available information, it's 28 grams per mole. So the question is it possibly CH4, CO, or Cl2? Okay, very good. Carbon monoxide. Okay, carbon's 12.01, oxygen 16, so 0.00, that's 28.01. So 28 grams per mole is closest to the molar mass of carbon monoxide. So that's how you can determine the molar mass of a compound. Okay, sure. They need to copy the answer. Okay. Okay, we're ready to proceed? All right. Now, uh, if let's take a look at this formula right here. Molar mass, we said, was mass divided by number of moles, right? And number of moles is PV over RT. Okay, so let me rewrite that. Molar mass, M sub M, is mass over number of moles, right? So I'm going to substitute for number of moles PV over RT. So instead of writing number of moles here, I'm going to write PV over RT. I'm going to make a substitution. PV over RT. And if I'm dividing by a fraction, what do I do with that fraction? I can flip that around and multiply instead. So that becomes M times RT over P. Okay. RT over PV, right? But I know that mass divided by the volume is just the density, right? So I can rewrite this. Mass divided by volume is just density. So that's just density times RT over P. So molar mass would be equal to the density of the gas times RT divided by P. And this is a common procedure used in the lab. This is used in the lab to determine molar masses of gases. You simply measure what's called the vapor density, the density of the gas. So if you know the density of a gas at a given temperature and pressure, all you have to do is multiply that by RT over P, and that will give you the molar mass. So the experiment that we do in the lab to measure molar masses of gases is known as the Duma method, or the vapor density method. Okay, so in a typical laboratory situation, you have something like a glass bulb, okay, with a little tiny hole right here. Okay, and you fill it with a liquid, and then you vaporize the liquid so it's completely turned into a gas. So you stick it in warm water, in hot water actually, boiling water. And so once it reaches 100 degrees Celsius, what you do is you just seal off this end right here. Okay, and so you can measure the mass of the you can weigh the bulb before and after. Before it's just filled with air, and then after you've sealed it, it's just filled with the gas. And then based on that, you can determine the mass of the gas. And then you would fill this up with water to determine the volume of the gas. And then you know the prevailing barometric pressure, and the temperature of the gas is 373 Kelvin. Okay, so that's the way you would do it in the lab. You measure the density of the vapor. Okay, now if you note that if you remember RT over P, okay, PV equals nRT. If you look at RT over P, if you rearrange this, okay, then that's just, I'm just going to divide this by NP. That will get rid of N from this right hand side and P from this left side. So this becomes V over N equals RT over P. So this expression right here, RT over P, is really nothing more than the molar volume. Okay? So RT over P is the molar volume of a gas. And we know what that is at STP. What is that RT over P equal to? If we plug in the value of temperature and pressure at STP, then that molar volume is just 22.4 liters per mole. Okay? So you can also say that the molar mass is equal to the density right here times RT over P, which is the molar volume. Okay, and this is particularly useful if you can measure your volume of your gas at STP, then you can, the density of the gas at STP, then you can easily solve for the molar mass, because you know that the molar volume at STP is 22.4 liters per mole. Okay, and here's another way of looking at this equation. If you rearrange this, you divide both sides by molar volume, you can see that density is molar mass over molar volume, which is really what the definition of density is. It's mass divided by volume of a particular sample. So if you have a mole of your gas, divide the mass of that 1 mole by the volume of that 1 mole, you get the density of the gas. Okay? So right here, the density is molar mass over molar volume. Okay. So let's apply that to this problem right here. The density of a gas at STP is 3.17 grams per liter. What's the molar mass of the gas? Very easy to solve. All you have to do is say molar mass equals density times the molar volume. So what's our density? 3.17 grams per liter. And our molar volume at STP, molar volume is 22.4 liters per mole. So all you have to do is multiply this by 22.4 liters per mole. Okay, so liters cancels out, and you have 3.17 times 22.4 is 71.0. Okay, so you may not be given the actual mass and volume, but you may be given in the problem the density of the gas. That's all you really need, just the density of the vapor. Okay, so density of the gas multiplied by RT over P. Okay, and so remember, this molar volume, you can calculate that from RT over P, but RT over P is just 22.4 liters per mole at STP. Now, if it's closer to room temperature, that would be around 25 liters per mole. So if you want to be able to estimate, okay, if you know the density of the gas at room temperature, just multiply it in grams per liter, just multiply that by about 25. That will give you an estimate of the molar mass of the gas. Okay? All right. And here's another problem, another example. This one deals with a mixture of gases, okay? And so if you did this type of experiment for a mixture of gases, you can get the molar mass you get would be the average mass per mole of your mixture. Okay, so in this particular example, it says ignore trace components and assume that air is made up of only nitrogen and oxygen. And you are asked, what are the mole fractions of nitrogen and oxygen in the air, given that its density is 1.29 grams per liter? So from this 1.29 grams per liter density at STP, we can actually figure out what fraction of air is nitrogen and what fraction of it is oxygen. Okay, and that's assuming everything else in the air is negligible. It's primarily made up of nitrogen and oxygen. And the way you would do this, you do a little algebra, you say, let's say you have a mole of mixture, okay, and let's say the mole fraction of oxygen is X. So if you have 1 mole of mixture, then moles of oxygen would be X, right? And the moles of nitrogen would be 1 minus X. Okay? If you have 1 mole total, X of those, X moles would be oxygen, 1 minus X moles would be nitrogen, because your mole fraction should add up to 1. So mole fraction of oxygen plus mole fraction of nitrogen should add up to 1. So if we're going to call this X, then this thing has to be 1 minus X so that they add up to 1. Okay? Now, if you know that the moles of oxygen is X, then you can calculate the mass. How do you get the mass if you know moles? You just multiply by the molar mass. So this is going to be X times 32.00 grams per mole. That's the mass of your oxygen. And the mass of your nitrogen would be the number of moles of nitrogen, which is 1 minus X, times the molar mass of nitrogen. Molar mass of nitrogen is 28. What's the molar mass of nitrogen? Let me see. Nitrogen is 14.007. Okay. 14.007 times 2. So 28.01 grams per mole. Okay, so times 28.01 grams per mole. Okay, so now all we have to do to solve for x is to find an equation that involves x, and that equation would be the one that says that the total mass is 28.9 grams. So in other words, we say that mass of oxygen, oops. In other words, we're going to say that the mass of oxygen, which is x times 32.00 grams per mole, plus the mass of nitrogen, which is 1 minus x times 28.01 grams per mole, must be equal to the total mass, which is 28.9 grams per mole. Okay? If you have a mole of oxygen, this is the mass of that. And if you have x moles of oxygen, you have x times 32 would be the mass of oxygen. And the moles of nitrogen is 1 minus x. You multiply that by the molar mass of nitrogen. That's going to give you the mass of nitrogen. So this is the mass of oxygen in 1 mole of your air. And this is the mass of nitrogen in 1 mole of air. This is the mass of the total of nitrogen and oxygen. So this is the mass of the air. And you can see my grams per mole will just cancel out here. Okay, the unit. So you have reduced this a simple problem in algebra. You can just say 32.00 times x plus 1 minus x times 28.01 is equal to 28.9. Okay, so how do you solve for that? Solve for x. That would be our x in this case. Can you work out the algebra for me? X should be a number between 0 and 1. So what would this be? 32.00x plus, okay, I'll do a distributive property here. That's 28.01 minus 28.01x equals 28.9. Combine these two. That gives me 3.99. Right? Let me see. 32 minus 28.01. 3.99x plus 28.01 equals 28.9, and then I subtract 28.01 from both sides. That will give me 3.99x equals 28.9 minus 28.01, 0.89. And so x is equal to 0.89 divided by 3.99, and that gives me 0.22. Very good. Okay, so mole fraction of oxygen is 0.22. Then 1 minus x would be 1 minus 0.22. Oops, 1 minus 0.22 is 0.78. Okay, so air we say is 78% nitrogen. So the mole fraction, this is the mole fraction of oxygen, 0.22. And then the mole fraction of nitrogen is 78.78. So it's 78. We say air is 78% nitrogen and about 22% oxygen if we assume there's nothing else there. Okay, so that's based on the density of air at STP given as the molar mass given as 28.9. Okay, how did I know that the molar okay how did I know that the molar mass is 28.9 actually? You may I think the given density is 1.29. How do I get from density to molar mass again? What you would have to do is you would say the molar mass, if you recall, is the density times RT over P, right? The molar volume is RT over P. Our density is 1.29 grams per liter, and the molar mass at STP is 22.4 liters per mole. So in case you were wondering where that 28.9 came from, then that's where it comes from. Okay, so 1.29 times 22.4 liters per mole gives you 28.9 grams per mole. Okay, let me verify that. 1.29 times 22.4, that gives me 28.9. Okay, so that's how you determine molar mass from the ideal gas law.